Hello, welcome to another online meeting for Discrete Mathematics. Um, so uh, this, what we, so let's just have a rest, think about where we're up to in the subject. So we've just finished assignment one. So lots of people put that in on time, so thank you. So it's in the process of being marked, and I'll get it returned when the marker gets around to finishes it. He's in the process of doing it. Um, the so how we've got it. So um, the sort of subject's broken up into five sort of sections. So the first section was really looking at sets and logic. Hello, someone coming in. So sets and logic and proof. So that was the first section. That was the first assignment. The next section we're doing is looking at um, counting, essentially, and the related concept of probability. So they're the main ideas. And counting corresponds to both counting with different bases and counting in the sense of combinatorics. So combinatorics is just a fancy way of saying counting, and it really just means counting the number of different objects we might consider on different things. And so that's really useful um, when you're trying to work out, well, how many different perhaps potential graphs might we have, or how many different possible connections might we want to consider. And if you want to do traveling salesman problem, all sorts of things, just how many different possible things can there be? And you might want to know these things because if the answer is small, you go, okay, fantastic, I'll just do a brute force. I'll just check all the options and see what happens. If the answer is really big, then you go, well, that's not going to work. I've got to try something else. And so just having a sense of how big or small, how many different options there are is helpful. So that's the big picture. So we're in the middle of that. So what I've done in lectures so far is look at different bases, spent a bit of time just looking at this counting bit, and I've just started probability, which is essentially just an application of that counting principles. So what I wanted to do today was really just recap some of these counting principles and just do some of the examples that I was doing in the tutorial for the internal students. Now, in the tutorial, the students were mostly doing the work, and I guess that's what I'm going to try to encourage you guys to do today. So you can try to tell me the answers as much as you can. Just something else that I've got to say. Which I've forgotten, unfortunately. No, I'll come back to my mind later. So if you've got any questions, fire away. So as I said, I'm going to try to get you to do some work today. And if you're not quite sure, that's okay. I don't exactly know where you're up to, but that's fine. To fire away. So as you can see on my slide here, I hope. Yep. We want to just try to count things, essentially. And when you're counting stuff, you want to count two sorts of things together. You want to be able to combine them. And so just like we have for sets and logic, we have sort of two key ways of combining stuff, and an OR. And again, we all have knots as well, so you might want to consider not something at the same time. So they're very similar sort of operators to sets. And the reason for that is because you can correspond all these sort of things to sets. So you really are just counting a bunch of options, and you can have a set of all the options. You want to try to merge the sets in different ways. So the OR really does correspond to a union in that sense of sets. The AND is different. It's not truly an intersection. It's something other than that. But it gives you similar sort of ideas. So basically we come up with two principles from it, and these are the special cases really. And I'll explain what the special cases are more as we go on. But basically, if you want to make M choices over here and N choices over here, and we want to do both at the same time, so choice 1 and choice 2, if you want and both of them, then normally you just do multiplication. Now, that technically is only possible, so that's a special case, that's only possible if the two choices don't impact on one another. So if they're independent of each other in a stat sense. I'll mention the word independence in lectures next week. I mean, essentially, though, it means what it's what you probably think it to be, and it is if you make a choice over here, in choice 1, that has no impact upon the choice you make over here. So an example where that would not be true is if you want to say you're picking in words in English, for example, and you've got to pick the first letter and then the second letter, etc. So you want to pick some letters and you want to make a word up in English. So the first letter you pick, well, you can pick anything. So if you want to pick a word of length 4, for example, well, any letter can start a word of 4. But if you pick the first letter to be Q, for example, then the second letter really is forced to be the letter U in almost all English words. There's not many choices around at all. And so there's a dependency. The two choices you make are dependent upon each other. There's not many choices. So this multiplication principle really is a special case, but that's fine. That happens very commonly. The other one is the multiplication rule. And again, if we want to make some choices over here or some other choices over here, then we want to add them up. Again, it's a special case. Again, you can't have anything in common. So they're going to have none of the choices over here, no choices can be shared. And essentially that means that there's nothing in common. Fancy ways we've used that is called disjoint. So in terms of set, so it's no intersection, or mutually exclusive. So they're the two main ways of trying to combine everything together. And so what normally happens is if you're trying to count something, you try to break it down into a bunch of disjoint situations, which are easier to count. So you'd use the sum rule to split up into a bunch of sums of things. And for each individual part, you would use the multiplication principle or something like that to try to work out how many there are for that situation. That's the basic ideas. So some things, what you have to worry about is that sometimes when you're counting, you overcount stuff, and you have to might divide by the number of ways of overcounting it, for example. And that's a special case, and that's where things like combinations crop up, etc. So I'll mention more of those as we go through it. So the last sort of the special case is if you want to, if you've got n elements, you want to order all n of them. Then there's a formula called n factorial that allows you to do that. And effectively, that's a button in your calculator. So 3 factorial would be 6, for example. So that's sort of the general theory. This is just, so there's some special cases, really, that apply to this very stuff. That's called permutations and combinations, which is these ones here. But I just wanted to put them in context just to give a sense of how you might pick ones from another. So the previous stuff I mentioned in lectures, but this is just a sort of summary of what I've done. It's a little different. So essentially, lots of these problems end up amounting to trying to choose m things from n, effectively. And so I've got bottom down. Let's make it concrete at the bottom. I'm going to choose 3 things from letters. So essentially, I want to pick 3 letters from A, B, C, D. You can pick them in different ways, and how you pick them differently creates different sort of objects, and therefore there's different numbers of them. So the first case is the ordered one, so where we actually care about the order you write them down on the page. So if you're happy to write, you got letters, so you're going to have 3 different letters. So if you're writing on a piece of paper, that ends up being a word. If you allow the letters to be reused, so with replacement, they really just produce different strings. So AAA, AAB, AAC, etc. So all the different possible strings you can make with the letters A, B, C, D. All different words, if you put it that way. That's called, and basically the way to do that is you got, for the first letter, you've got 4 choices in this case. The second letter, you've got 4 choices. The third letter, you've got 4 choices. Each of the letters have no impact upon each other, so they really are independent. So it's 4 times by 4 times by 4, or in short, 4 cubed, which is 64. And so in general, the formula is the number of choices for each letter to the power of the number of letters you want, effectively. So it's sort of a general, that's really just the multiplication principle straight as, essentially. That's counting strings. Another case when you want to do order is when you want to have order, but you don't want to replace letters. So you want to just have every single letter is distinct from each other. And that's called a permutation. And so an example is ABC, so you have no repetition, as you can see here, or ABD, so again, no repetition. So these are all different ways of rewriting the letters A, B, C, D in any particular order, but just three of them, and they have to be different letters. So it's just really counting the number of orderings. So permutation is just another way of saying ordering, really. And so there's a button in your calculator called P, stands for permutation. So NPM or NPK, I think is how it might describe in your calculator. Um, and what it really means is how it works is you go, well, for the first letter, I've got four choices. I've got nothing to pick. For the next one, I want to make it independent. Is this next choice is, well, I've only got three choices left. I've already picked one, so I've only got three choices left. So it's 4 times by 3. And then last one, you've only got two choices, so 4 by 3 by 2. And that's effectively how the calculator works out a permutation. Now, this is not the application of the special multiplication rule. It's something else. It's more the general one. But you understand it. I mean, it's sort of one choice and the other. And we've made sure that they are not going to overcount or something like that. So that's counting in order. But we might also sometimes want to look at situations where we don't really care about the order. We just want to consider about the collection we have. And so we just want to, do we have them or not have them? So just do they contain or not? There's two examples of that. You can do with or without replacement. The only one I've done in class is the one without replacement. So that's what I'll consider. But I mean, I've put it here for completeness that you can do other things, and it is related just to combinations again. But the one I want to focus on is you don't care about order, and you're just going to pick them. So basically, I've got a bunch of letters A, B, C, D, E. I want to pick three of them, but I don't care about the order. So that really just amounts to picking three as a set. And so it's really just a picking a set of size 3 is one way I think about it, or just a collection of size 3. And so I can actually write them all down. There's not that many choices here. So if you're picking 3 letters from 4, it means you're leaving one behind. And if you're leaving one behind, there's just 4 choices for what leave behind. So there's just 4 options. And the answer in terms of your calculator is 4, choose 3. And again, your calculator can happily tell you that. So just recapping, really is a combination is when you really don't care about the order when you're picking stuff, and where permutations order makes it matters. That's the big difference between the two, which I think is the most helpful thing. Although that's the idea, they might come up in surprising ways at various times. And there's certainly lots of sophisticated tricks about how to do it, which I'm not going to teach you all of them, but some of them are useful for this sort of subject. So that's the basic theory. Let's look at some examples if I can ever get my stuff out. So just so here's the first few questions. So this is where I want you to try to do some stuff. I'll happily confirm or talk about any questions you've got. So the first one is question 1. So fire away, type your answer in when you got it. But while you're thinking about it, I'll just say a few things. So it says, how many possible outcomes for first, second, and third are there from a 10-horse race? So I'm hoping you can get the answer. But just things to think about is I've currently got 3 options here. So I'm selecting 3 stuff, and I'm picking them from 10 horses. So I'm selecting 3 from 10. So questions I have then is there an order to it? So and you go, well, if you're picking first, second, third, yes, there's an order. So they're ordered. So order is important here, which really does tell you what it's going to be. And the second thing is when I pick the horses, the same horse can't come first, second, and second and third. You can't just have repeats. So this is really, there's no repeats. So this is without replacement is my fancy way of saying it. Now, you don't have to think through these things, but I think a really key idea is to realize that we're trying to order 3 horses from 10. And as soon as you're trying to order 3 horses from 10, then we were doing things in order without replacement. So really, it's just going to be a permutation. So that's what it's going to be using this sort of formula. And so therefore the answer is going to be, I've got 10, I want to permute or order effectively 3 of them. So that's the answer. Can you guys pull out your calculator? It's probably good practice. And just see if you can find what it's going to be. So 720, so I reckon. Thanks. So if you didn't use your calculator, another way of doing the same question, so in blue, is I've got 10 choices for the first horse. Once I pick the first choice, I've only got 9 left for the next one. And the third horse, I've got 8 choices. And multiply that and you get 720. That's exactly how your calculator's doing it. So thanks very much. Let's look at the next question. So this is, so I don't know where you are, but I live in the Central West, and so my electorate is the Clare, and so we're about to have a by-election for the state because our state, so the state MP decided to go to the federal parliament instead. So we're about to have a by-election, and so I don't have any candidates, so 6 or 7. So let's assume we have 6 candidates in the council by-election. The order on the paper, the ballot is randomly selected, just not to give anyone favors for having really last time being A, for example. So how many different orders are there possible? So you can see we're counting orders. So again, order is going to be important in this situation. And how many we're ordering? Well, we're ordering all 6. So you can do it a few different ways. So I just really want to order 6 things, and you can just do it that approach. Another way is I really want to pick 6 from 6, and again I want to have an order, and I don't really want to replace anyone. No one's going to be twice, and so it's going to be, depending on how you think about it, if I order all 6, that's called 6 factorial. So ordering just a whole number of things is that number of factorial, or selecting 6 from 6 is a 6. I want to permute all 6 of them, which is the same answer. What number do you get? In the case. Yep. And so both times you get 720. So they give the same answer, which looks the same as the past one, but for quite different reasons for that matter. Okay. So the next question is, I've got a bunch of 8-bit strings, so that strings of form, 8 binary digits essentially, and so 8 digits, and each of them can either be a 0 or 1. So that's a common word you'd see in, so a common word in a computer tends to be 8 bits. So what I want to do is, how many of these bit strings contain 4 ones? So if you think about what I'm doing here, so that's 3A, I really want to select, select 4 from 8 to be a 1. That's what I'm really trying to do. So I'm trying to select some of them. So select some of these. So I've got 8 different bits. I want to select 4 of them to be 1s and 4 of them not to be 1s. And so the question is there with or without replacement? Going, well, I've got 8 different positions there. I can't pick the position more than once, so it's certainly without replacement, so I don't have to worry about that one. Does the order matter? So really I'm just picking different positions. So I've got positions 1, 2, 3, 4, 5, 6, 7, 8. Which the order I pick the ones in doesn't really matter. It's just what positions they are. So there's really order does not matter effectively. And what I mean by that is, what I'm really selecting is I'm selecting the positions. So 1, 2, up to 8. And if I picked position 1 and 2, so if I picked positions, so for example, I picked 1, 2, 3, 4, or if I picked 4, 3, 2, 1. So if I picked either of those positions, the corresponding string you'd get would be, well, I'm picking the ones. So positions 1, 2, 3, 4 are all ones. The rest must be zeros. If I pick 4, 3, 2, 1, I'll get 1, 1, 1, 1, and a bunch of zeros. So although I pick the positions in different orders, you get the same string, so there's no difference. So that's why order doesn't matter in that sense. And so selecting 4 from 8, order doesn't matter. There's no replication. I'm just basically, the answer is going to be 8, and I'm choosing 4 of them. So when I'm selecting with order, permutation, selecting without order, like in this case, it's 8, choose 4. What's that equal to? 8, choose 4. And again, you're going to find the button in your calculator. So 70, if someone says, thanks. You everyone okay with the logic before you get to 70? I mean, So in your assignment 2, so assignment 2 covers these questions among other things. You're gonna have to type in the answer. You're really gonna have to type in something like 70, for example. In your final exam, where it's gonna be someone hand marking rather than computer, I will accept things like 8, choose 4, etc. That's what I'm looking. So that shows you understand the sufficient logic. In an exam 2, say you write down the answer 70 and got if you wrote down just the answer 71, for example, and I go, well, that's wrong. But if you write down some working indicating where you got the 70 or 71 from, I go, oh, look, you really just did 8, choose 4 and you just typed it or something like that. So I can give you a partial mark. So make sure you include working when it comes to an exam situation. What about 3B? So all of them so far, so 1, 2, and 3A, really are just just thinking about when you're picking stuff, whether they have order or not, when it comes down to it. So 3B is a little different, and that is how many bit strings of length 8 contain at most 4 ones. So this one's not such a simple case. So the first thing I have to do, really, is I have to convert at most. I have to understand what it means. So what does at most mean? So in terms of inequalities is probably the easiest way of saying it. So what is at most in terms of inequality? So in terms of less than, greater or equal to, less than or equal to. So the choices. Which one would you pick for it? Don't be shy. Someone's having a go. Yep. So it really means less than or equal to. And so, as you correctly said, so for 3B, we either want to have, so less than or equal to 4, essentially is what we're aiming for. So less than or equal to 4 ones. And so you think through the options. So you're either going to have 0 or 1 or 2 or 3 or 4. So they're my different choices. So they're all the different numbers I can perhaps have. And so really, and each of those cases are disjoint. So none of them can happen at the same time, which is really important when you're splitting up into cases. And so I just want to count each case separately, really. So the first case, I've got my 8 different positions. I want to choose none of them to be a 1. Alternatively, so I want to sum, otherwise I'll have 1. So out of my 8 positions, I want to choose one of them to be the 1. Or I can do the second position, or I can pick 2 to be 1s, or 3 to be 1s, or I could pick all 4 of them. I'll say not all 4, so I could pick 4 of them to be 1s. So that's pretty much what my expression is going to be. So I want to consider all the different possibilities. So for each possibility, work out what it is and just add them all up. And that works nicely so long as the cases are what I call mutually exclusive or disjoint. So see if you pull out your calculator, see if you can get the answer. So while you're typing in your calculator, I'll just talk briefly about 3C. So for 3C, you do the same sort of thing. And at least means greater or equal to. So you want greater or equal to 4 ones. And you can do it the same sort of way. So you could list the numbers would be 4, 5, 6, 7, 8, and do the same sort of sum for that one. You can do it quicker, and that is at least 4 ones means you have um, at most 4 zeros, and that sort of balances out. So if you've got at least 4 ones, you have at most 4 zeros. Zeros and ones are completely symmetric in the problem, so therefore the answer to C and B are going to be equal to each other. And as someone said, that's 163. So 163 is correct. So the answer for 3B and 3C are actually the same number. So you can see how you're splitting up the case in that case scenario. Okay. Cool. So thanks very much, guys. So next one is we'll look at how many permutations and how many orderings are there of these letters. I should fix my typo up. Not a very good at fixing a typo, is it? How many permutations of these 7 letters will contain the string ABC? And when I mean contain the string ABC, that means in that order. So the way to approach this question is pretty much I'm going to group things together. So ABC really is just considered as one big group. And then the other letters, starting with D, E and F and G. So these other letters are really their own group. So their own group by themselves. So that's my groups. And then now I've got my groups, I then want to order them. So I've got, how many groups do I have? Well, I've got 5 of them. So I want to order my 5 different groups. And so how many different ways are there of ordering 5 groups? What do you guys reckon? Started typing and it didn't work out, come through. Excuse me for a second, I'm about to cough. Sorry about that. I had to just mute it myself so I didn't get blasted by my cough. So, how do you? So you got 5 things effectively, so 5 groups, and we want to order 5 groups. So we got 5. Now you can think of it different ways. So I just want to say I want to order them. So I just want to order 5 things. We'll just make it 5 factorial. Otherwise, as described before, I've got 5 things. I want to pick 5 of them in order. So it's also equal to 5 P5. So picking 5 things in order would also be the same. They're the same. I would normally just write the first form down. What's that equal to? So 120. So maybe you knew that already and just weren't too shy to say. That's okay. Yeah. So what about the second situation? So what about 5B here? How many different permutations are there if you want to insist that A, B, and F, G, A and B have to be next to each other and in that particular order, and F and G have to be next to each other and in that particular order? How many different ways are they producing this time? The answer is the same, that's right, because effectively you've got A, B, F, G, you'll have C as its own group, you have D as its own group, and F, G, so and E as well. So you'll still have 5 different groups. The groups are different, but it's still 5 groups, and there'll still be 5 factorial ways or 120 ways of ordering those 5 groups around. So it's the same answer. That's right. Okay. So next one is about picking committees. So essentially, we've got 10 people, and we want to pick 7 of them to form a committee. And we're just going to pick them at random. However, we want to just pause for a second. Is that we want to try to get some sort of and be thoughtful at least about what the potential gender bias, if anything, there might be when it comes to the committee. So, what are the chances if you pick a random committee of having more women or more men, etc. So that's ultimately the question is. So let's do it at a simpler case at the moment. We have to worry about the genders. So I've got 3 men, 4 women. Um, let's just do this case. So I want to get the committee of 7 people. I want to have 3 men in it and 4 women in it. Just how many of different ways are there of doing that? And then you can answer things like probability later for it. And essentially, when you're picking a committee, there really is not an order to it. Like you're just picking a bunch of people. The fact if you pick Joe before Bob, doesn't matter if you pick Bob before Joe. Essentially, at the end of the day, you get the same committee, same group of people. So order doesn't matter. So order does not matter. So for 6A, you're going, well, I've got some men, so I've got 4 men. I want to pick 3 of them, and since I don't care about the order, it's going to be a choosing. So I'm choosing 3 from 4 without order. And for women, I've got 6 of them. I want to pick without order 4 of them. So they're my 2 different numbers. So some questions I've got is, what are the numerical values? But what do you do? So should you be doing multiplication or plus? Which of those 2 different cases should you do here? So plus would imply that you want to do one or the other. Multiplication if you want to do one and the other. And since we really do have the word and here, that would tell me that we should do multiplication, just like someone typed in. So you want to multiply the 2 together. So now it's just a matter of trying to put your calculator out. So 4 choose 3 is equal to what on your calculators? So how many ways are there of picking the 3 blokes from 4? So the answer is 4. So it's 4 times 6 choose 4, which is equal to what? So 15. And then 4 15, your calculator can tell you is 60. So there's 60 ways of just picking a committee of 3 men, 4 women. What about 6B? How many ways are there of picking a majority of women? And the answer is, well, there's a few ways of doing it. So there's more than one way of doing it. So what I would do is I would split up into cases. So these are different. So I want to look at the different cases and then work out, just like if 6A, how many different ways are there for each different case. So first of all, what some of the cases? So we've got to have men and women. So give me a case. How many men and women would you have to get a majority of women? So which means more women than men. Okay, so you can have 3 men, 4 women. That would be a majority. Yep. What other cases can there be? Just waiting for people to type in. Yep. So 2 men, 5 women. Anything else we can do? Yep. So 1 and 6. Anything else? And you would go, oh, let's pick 7 women. And hold on a sec. You can't do 7 women because there's only 6 of them. So Um, so that's it, really. So that ends up being the end of the day. And so they're all the different cases that we can consider. And so therefore we want to do the number of ways for each of these cases. And the same sort of approach. So the first one we've done already. So there's 60 ways for the first one. We've already done that. And the same sort of approach for the rest of them. So we want to have 4 choose 2, so I want to pick 2 men from the 4 times by, it's the same sort of approach. Out of the 6 women, I want to choose 5 of them. And I'm going to work out the number. And for the last case, what would it be? Maybe you guys can tell me. So how many different ways are there for this last case over here? So we have 1 guy and 6 women. So why I'm getting you to do all the work is because you learn more from having to do it yourself, essentially. And that's what the real goal is here today. So some people are listening to the recording, I would hope later. And so for those people, I encourage you also to, while you're waiting for pauses, actually try to fill in things yourself. So how many different ways? So for this last case, I really have got 4 men. So, and I want to choose one of them. 4 choose 1 is 4. So I actually have 4 choices. So I have to pick one. Basically, I have to pick a guy to make up the group. So there's 4 ways of doing that. I have to pick from my 6 women. I have to pick all 6 of them. Well, there's only one way of picking all 6 women. That means everybody. So really, in this last case, there really is only 4 choices, and the choices really is about which is the man you pick to make up the numbers, essentially. So that's the last one. So only 4 is the answer, but that's how you write it down. For this middle one, 4 choose 2 is 6, which is perhaps what you're writing down. And then 6 choose 5. Basically, I want to pick 5 women from 6. So you have to pick the lady that you don't want to include, essentially. And so there'll be 36 ways for that. And what I want to do then is I want to sum up each of these. So I've got 60 for the first case, 36 for the next one, 4 for the next one. Add up these numbers, gives me 100. So I'll have 100 different possible ways of picking a committee in this particular situation where I've got more women than men in it. Now, 6C is the same sort of idea, very much the same idea, and that is I would like to just list all the cases again, but this time not for majority of women, but this time with a majority of men in it. So I'm going to think of all the different options. I've got to think of how many ways that would be for each option, and then sum them all up, like I did a second ago. So same approach. So how many different men and women would we have to get a majority of men? Yep. So, and as you just said, the only way of doing, there's only just one case, you have to have 4 men, 3 women, that's it. And the reason that's all that thing works is because there's only 4 men to pick from. And so the number of ways of doing that is I've got to choose all 4 men. So there's only one way of doing that. And then, so and means multiplication, and I want to pick from my 6 women, I want to pick 3 of them. And there's 20 ways of doing that. Your calculator can tell you. So, therefore, in total, we only have 20 different ways of picking a male majority. So 100 ways of picking a female majority, 20 ways of picking a male majority. Which is not surprising, probably because you've got more women than men in the first place. So that makes sense. So that's just looking at different ways of combination. So again, that just shows you the idea of splitting things up into cases and using that multiplication principle for each case separately, and then adding them up using that or sum principle at the end. So there is a sort of they're all the sort of cases that I would normally get you to consider to do. So I have one more question in the tutorial here. Now this one is much harder. And so being much, much harder, I would certainly not expect you to do this in an exam or even in the assignment. So it's quite a bit harder. So you can take it or leave it, I guess. But we'll just talk through it just to show that the basic principles that we have still can handle the harder problems. You just have to be thoughtful in your splitting up a case. So basically what we have here is we've got a 5-horse race, so just 5 horses. And how many different ways can they finish? So essentially, how many different ways can you order 5 things? So at first glance, you think the answer is going to be, oh, just 5. Ordering 5 things would be 5 factorial equals 120, that's it. But what if we allow ties? What if we actually consider the situation that maybe they can tie? That allows a lot more possibilities. So what I need to do really in this case is to consider different cases. So I'll talk about a pattern. So the first pattern really that we consider is, say, no ties at all. Then we're going to have some orderings for it. So first of all, I'll talk about so I have patterns, and I have to talk about the number of patterns you might want to consider. I'll explain more what I mean by that in a second. So for no ties, there's just really no one way of getting no ties. Just no ties. Number of orderings would be, as I said, 5 factorial, which is 120. So if I do the product of these two, so I want to know the number of patterns and the number of orderings. I want both at the same time. So I'll just do the product of the two to give me 120. So the first case I've really got produces 120 different ways of trying to finish this 5-horse race. But there are other sorts of patterns we can consider, and that is we're going to have some sort of ties. So you can rattle off one. What other sort of, how else can you have some sort of pattern you can have? And then we'll try to split up that case. And each case you present has to be different to all the other ones. So you have to split up your cases in such a way so that they're all mutually exclusive or disjoint. That's really critical. This one gets complicated, and so at the same time, you want to make your cases a bit as generic as you possibly can, just to save a bit of work for you. So that's why I've got this number of patterns idea cropping up. So any suggestions? Just waiting for people to think through it. Yep. Okay, so we're going to have a 5-way tie. That's right, it's another pattern. And again, for a 5-way tie or 5-horse tie for first place, there really is just one way of sort of satisfying that pattern. Again, it's a pretty distinct case. How many different ways are there of ordering those horses? 2 ways of thinking about it, as in, if all 5 horses tie for first place, they're all coming exactly the same time. There really is no ordering between them, and the answer is just going to be 1. So that would be it. Another way of thinking about it is, I could actually order all 5 horses to 5 factorial. The problem is, because there's a tying there, I'm overcounting big time. The number of times I'm overcounting would be the number of ways of ordering those horses within the tie. So if I divide the number of ways of ordering them within the tie, 5 factorial would give me the right answer. And why I write it that way is just so you can see the patterns of the rest of them. But the answer is 1. So it's 1 times 1. There's just one way of getting a 5-way tie, essentially. What other options are there? So let's just put the patterns down. So no ties would be that sort of pattern. 5-way tie would be all of them come together at the same time. Any other patterns you can think of? Something in between a no tie and a 5-way tie? So this is the harder part because you have to try to think of something. So a two-way tie. Um, so we have one two-way tie. I guess will be the next pattern. And so that could be, so as an example of what that might look like, that could be, so first and second could be tied, and then all the other places are distinct from each other. But I guess we want to try to count them in different ways. So you can have first and second tying, or you can have second and third tying, or third and fourth, or fourth and fifth. So there's four different places where you could get the two-way tie happening. So there's sort of four different patterns we want to consider at the same time. That's really what I want to consider here. So instead of, so two-way tie is a good way of describing it, so thanks. And just sort of go, well, there's four different ways that all have the same pattern. How do you count them? So this is the key one. So again, you've got the five horses. So at first glance, the naive approach is let's just order the five things, so five factorial ways. But the problem with doing that is that in the example pattern, so first and second are tying, if they're tying, then you can't tell them apart. So if I swap horses one and the horses go for the first two places, I swap them around, you get the same situation happening. And so I really got to divide. So what I'm really problem is, if I'm doing 5 factorial, I'm overcounting. So I need to divide by the number of ways I'm overcounting. And I'm overcounting by a factor of 2 because I can swap the order. So two different ways. I'm overcounting by a factor of 2. Or in general, the number of ways of ordering this first little group around. So I've got to divide by 2 factorial, which gives you 60. And if you do 4 times by 60, gives you 240, for example. So that's another pattern. So now we're going to think of, you're going to start thinking of all the different patterns you might want to consider. So we've got a no tie, to one two-way tie, a four-way tie. What other patterns can we have? Yep. So we can have two two-way ties. So let's look at an example pattern. So two-way tie, another two-way tie, and then one by himself. The number of ways of getting this pattern really is just picking the position who's not tied. So whether it be at the beginning, in the middle, or at the end. So there's going to be 3 different ways of getting a two-way tie, two two-way ties. So either the guy not tied is the beginning, middle, or end. The ways of ordering that would be 5 factorial again. So just order 5 or 5 of them. But again, oh, hold on a second, I'm overcounting here. I can reorder the guys in the first two-way tie 2 times, and I can reorder the guys in the second two-way tie 2 times. So I'm overcounting by a factor of 4. So I'll give you 30 all up. And 3 30s gives you 90. The same sort of idea. Any other patterns you can think of? Pardon me. Yep, so you can have a full house, I guess you want to call it. So 3-way and 2-way. So 1, 2, 3, and 2. And you think about it, well, either you have the 3-way fly at the beginning or the end. So there's just going to be 2 ways of doing that. And similar, so you've got 5 factorial divided by the number of ways of ordering the guys in the first group. So 3 factorial number of ways by in the second group. So that's going to be equal to 10. And so there's, take the product and give you 20 different ways of doing that one. That's the full house, so to speak. Any other ideas you can have? So if you think about it, it's all, so the first one is um, all different, 5 of a kind, pair, 2 pair, full house, 3 of a kind, so 3-way. And the last one you want to think of would be a four-way. That's the last one we need to do. So three of a kind and four of a kind in terms of cards. So three-way would be that sort of situation. Of four-way, look at that. So I'll do them at the same time. So for the three-way tie, essentially you've got to pick when the three-way tie can be. So it's going to be 1, 2, 3, 2, 3, 4, or 3, 4, 5. So there's going to be three ways of getting a three-way tie. Like all of them, it's 5 factorial divided by the number of ways of you can overcounting. So I'm overcounting it by 3 factorial because I'm overcounting with the three-way tie beginning here. So that's going to be equal to 20. And the four-way tie, I've got pretty much the guy by himself can either be beginning or end. So first or last, essentially. So there's just two options there. And the number of ways of ordering that would be 5 factorial divided by the number of ways of ordering the tie within the tie itself. And so you've got 5 different ways of ordering tie, just picking who the other person is essentially. So taking products, you get 60 and 10. And that's all the options, I think. So if you think of anything else, let me know. And so we can add them up. So if you add up all these numbers, you get, I hope, 541. Just something else to notice. If we add up these number of patterns here, so 2, 6, 9, 12, 16, gives you 16 here. That's equal to the power of 4. So there's something else that we might, there's something else that sort of underpins all this, and I'll just mention it just as an aside more than anything else. So when you've got no ties, that's really corresponds to picking it's 4 choose 0, I think it is. Four choose, so the 5-way tie corresponds to 4 choose 4. The 2-way tie is 4 choose 1. The 2 3s together is 4 choose 2. So 3 plus 3 is 6. In the last case, the two 2s together is 4 choose 3. Just explaining where they might come down to being. I've got the order around the right way. So where all these different things come from is for the 2, 3 cases, just to see the connection, you can see that in both cases, you really are just breaking the thing down into 3 groups. So 3 different groups. And the 2, 2 cases, you're breaking it down into 2 groups. So you can count the number of partitions. So number of partitions, that's the number of ways of breaking things up into different groups. So these combinations can be used as well to count the number of partitions and various stuff. And you can see what's happening, and that's what it's doing here. So, and if you got and therefore the total number of partitions you can have in this situation is 16. So there's other sort of patterns you can look at here if you wanted to go for it. Now that's beyond this subject, in case you're getting worried for a second there. But that's the idea. So just as a recap, that last example is way more harder than I really want to put in an assessment item, because you can know lots of stuff and not really know how to show it in that sort of example. But it does show that the basic principles we have still carry over. And that is, if you just break things down into different situations, just work out how many different ways of getting that particular situation and add them up, it gives a total way. The other sort of concept that I really introduced there, which I think is important just to emphasize, is this idea of overcounting and how to correct for that. So when I was trying to order this particular situation, for example, I overcounted because there's three that are really are effectively the same. And so dividing by the number of ways of ordering that particular group is a way of correcting that. And that particular concept is used in the formula for doing combinations, for that matter. But it's useful in other situations too. So that's the extra thing I did in that last example. So thank you very much, guys. That's the last question. So we did all of that exercise sheet today. So that's what I did in classes as well. So I hope that helps just to show what I'm doing for internal students, and hope you get your practice. But as I said, those first questions rather than last ones are sort of the level of difficulty and ideas that you might want to see in an exam or an assessment item for that matter. Just before we go, do you guys got any questions about this? Doesn't have to be any questions, but just things that crossed your mind as you've been going through these different counting ideas. No, that's okay. So thank you very much, guys, for attending, and I hope to see you next week. And if you've got any questions in the meantime, just fire away as normal. That's fine.